This chapter's video, chapter 21, is actually only going to focus on the first two portions of chapter 21 in Openstax Astronomy. We focus all of our attention on the other sections of this chapter when we talk about exoplanets. So really our main goal here is to set the stage for how stars actually form out of the material in the interstellar medium, which we talked about in chapter 20. So if we look back at the constellation Orion, we talked about Orion's nebula as being our classic example of an emission nebula, but the gas and dust in this part of the sky is a lot more than just Orion's nebula. So the Orion Nebula is here, the sort of scabbard of underneath the belt, but if we look at that in the infrared, it's part of a much larger system, a larger overall structure. This is a giant molecular cloud. So giant refers to the overall size of this object, and we'll talk about size in just a second. Molecular means that it's cold enough that the hydrogen atoms are actually formed into hydrogen 2 molecules, so 2 hydrogen atoms bound together. And that only happens when temperatures are really cold. And so when we look at examples of parts of the giant molecular cloud, so GMC here is giant molecular cloud, the central region here has a lot of brand new stars forming. Now, we're going to talk about star clusters coming up soon, but stars tend to form in star clusters, all stars, even ones that don't seem like they're in a cluster anymore, like our sun. When we look at the image on the left, it is not just visible light, it's enhanced color to highlight a couple of key structures. But what we can see is that it's actually hard to tell that there are stars embedded within that cloud of gas and dust. When we add infrared, like we do on the image on the right, we can see that deep within this cloud, there are a whole lot of stars grouped together. That's a star cluster. And they're all forming in Orion's nebula. The fact that that's an emission nebula means that there's a young O or B, very hot star. And so we're seeing stars as they're forming, and that's why we call that a stellar nursery. If we look at a larger example, so not Orion's nebula or that particular giant molecular cloud, but instead a different one. This is the Eagle Nebula. And if you kind of tilt your head, it looks a little bit like an eagle carrying like a fish or something in its talons. It's also called the Pillars of Creation because this is where stars can form. Now this object here on the left in part A is the overall Eagle Nebula. And in part B, we've zoomed in on the leftmost largest pillar. Now the size of a giant molecular cloud, the whole structure, can be 50 parsecs or more across. And I need to put that into perspective for us because that unit of parsecs we don't have a lot of intuition for. The unit itself, parsec, came from our discussion of stellar parallax in chapter 19. And 1 parsec is a little bit longer than than 3 light years. So it's like 3.26 light years, something like that. So 50 parsecs is a distance that would take light more than 150 years to get from one end to the other. To put this into a different form of perspective, from our solar system to the nearest star is 1.3 parsecs. And so this thing is a size that is over 30, 40 times bigger than the distance from us to the nearest star. So very large in size, and that means it comes with a lot of mass as well. We're going to use the sun's mass as a sort of typical benchmark throughout all of the rest of the slides, all of the rest of the chapters in this course, because there's no intuition we have for what 10 to the 26, 10 to the 30 kilograms, none of that makes any sense to our brains, no matter how much we want to try to understand that. But as long as we've kind of internalized the fact that the sun has a huge amount of mass, we can use it for comparing to other things. So this giant molecular cloud has a mass over 100,000 times the mass of the sun, which means if we collapsed it all down to make sun-like stars, we would get 100,000 of those sun-like stars. And then the temperatures are just a few Kelvin, so just a few degrees above absolute zero, similar to the rest of space, deep space between stars. Now, stars can't form at these really low temperatures, so they're not actually forming in any part of the giant molecular cloud, but rather in dense cores, so smaller parts of the giant molecular cloud that are a little bit denser, and they tend to be denser, a little bit warmer, and on much smaller scales. So 0.1 parsecs or 20,000 AU, so the astronomical unit, one of those is the distance between the Earth and the Sun. And 20,000 AU from the Sun outwards gets somewhere in the Oort cloud. So this is now on the order of a solar system-sized area. If we go back one slide and we look deeper at this part, picture B here, you can see some of these things have kind of globbed off into little blobs that each one of those is going to form a star, and that's what we're talking about when we talk about these dense cores. The dense cores happen to be slightly denser than the rest of the giant molecular cloud, but they can't fully collapse on their own. There's a lot of factors working against that collapse. Factors that we can't really get into in this course without going into much more complex physics than we require. But if a shock wave passes through those dense cores, they will start to collapse, and then gravity will take over and they can form a star. There's a lot of possibilities for what causes that shock wave. So when massive stars die, we're going to learn all about how the most massive stars are able to go supernova and cause huge explosions, which can then cause star formation in all directions around them. When massive stars are born, they ionize the gas around them, heat things up, and can actually cause a shock wave that way. And that's one of the reasons why stars tend to form in clusters, is if a massive star is able to form, then it can create star formation all around it, or a shock wave has passed through an area with a lot of these dense cores. Another possibility is when two or more giant molecular clouds collide with each other. So we'll be talking in many chapters in the future about galaxy mergers, and that can cause a lot of star formation as these large clouds of gas and dust that are 50 parsecs or more across, as those clouds collide, they cause a lot of star formation as well. Now, the collapse of a dense star, once it's triggered, we then let gravity take over, and gravity will take all that material and collapse it down. As it collapses down, it heats up, and we go into all of the thoughts we had back in chapter 7 when we talked about the solar nebula theory. This is the same theory, just generalized to all stars. Now, when we see this word protostar, what we're talking about is an object that will become a star. We can't just go around and call anything a protostar. But it is not yet a star. In the same way that a prototype of an invention is not really a fully working invention yet, the protostar is not really a fully working star yet. There's also a protostellar disk, so it's a fancy term for basically the disk of material that planets can form out of. Now, as the protostar contracts and gets smaller because gravity's pulling it into a tighter and tighter ball, the temperature gets bigger. It's turning gravitational potential energy into heat and light, so even though it's not turned on fusion yet, the protostar is still shining fairly brightly. It takes quite a while, actually, for the protostar to go from being a collapsed dense core to actually forming a star. And that's what this picture here is trying to show us. All of the numbers that are along the black tracks are values in years for the starting point of collapsing a dense core to actually turning on the star. We define the point when a star turns on as the point when hydrogen fusion is able to start working in the core. The core has to reach the high enough temperatures for that to work, but at some point that happens. Now, if we look at all of these different star examples, if we start at the very top, 100 solar mass stars, that's kind of at the limit of the size of stars we can make, and we'll talk about why later on. But we see that there's points at 100 years, 1,000 years, and by 10,000 years, it's ready to go. A lot of mass means gravity is very strong. Gravity can pull it into a ball very quickly, and then we have a star. For a star like our sun, I'm going to skip a few. You can always pause and look at this image in as long detail as you want to. For a star like our sun, we have points shown here at 100,000 years, a million years, and by 10 million years, it was able to turn itself on. Keep in mind, it's good that it took a long time, because in that 10 million years of the sun forming, that's when we were also forming the planets. And then for a 0.1 solar mass star, so a tenth the mass of the sun, it can take 100 million years of being a protostar, slowly contracting. Less mass means less gravity pulling on it, before we actually turn on fusion in the core. Now, back in chapter 16, we learned about the proton-proton chain. That was really important for us to recognize the name of it and kind of connect that with the sun. But all main sequence stars are turning 4 hydrogen atoms into 1 helium atom through fusion. Now, low mass stars, like the sun, use the proton-proton chain. We don't have to memorize the internal order, but what we did talk about was the fact that the end result is that 4 hydrogen atoms become 1 helium atom and energy is released. Back in chapter 16, we talked about what happened to those gamma rays in neutrinos, depicted here as the Greek letters gamma and nu. And we talked about the fact that this energy is coming out because there's actually less mass in that helium atom than there was in the 4 hydrogen atoms. What's important for us to add to our understanding now is that high mass stars are not actually going through this process. It's not a fast enough process for them. Instead, they use the CNO cycle. We do not need to know the internal order or steps to this cycle. It's not an important part of our curriculum. But what we do need to recognize is that higher mass stars use this other process, and so we need to connect the idea of CNO cycle with high mass stars and the idea of proton-proton chain with lower mass stars. Both of them turn hydrogen into helium. That's also very important for us. If we follow this chain around starting at the top middle, we see a carbon atom hitting a proton or a hydrogen atom. They smash together, and that whole process goes all the way around, where if we trace what's going into this, 4 total hydrogen atoms go in, and 1 helium-4 atom comes out. And so all of the other pieces here are carbon, nitrogen, and oxygen nuclei that are being recycled, reused over and over again, but we still end up with hydrogen being converted into helium through fusion, and energy is released. Same amount of energy, but this process is just faster. Higher mass stars need this faster process because more gravity trying to crunch them down means they have to push back out with a higher pressure. We talked about the phrase hydrostatic equilibrium back in chapter 16, and this is incredibly, incredibly important for us as we move through the rest of stellar evolution. That phrase hydrostatic equilibrium, if we don't remember it, we need to write it down in our notes now. It is the balance between gravity trying to pull everything inwards, so the force of gravity pulling stuff together, and the outward push of gas pressure pushing things out. So the pull of gravity balanced with the push of pressure. It's a really delicate balance, and the image here is kind of showing that towards the center of the star, The temperature's higher, so there's more pressure, but that's because gravity is stronger. Everything's more tightly packed, and so gravity's stronger too. The balance is happening at all of these different levels for a stable star on the main sequence. And a star with a certain mass means it's going to be going through its energy at a certain rate and have a certain temperature. And it really comes down to this idea of hydrostatic equilibrium as the reason why the main sequence is such a narrow band of stars. The mass of a star determines the rate at which it can go through its energy and the temperature that it's going to have at all of these different layers. And so it's kind of forced to be along that stable line. Now, for this hydrostatic equilibrium, we want to keep that in mind, not necessarily for the other videos this week, but for our later discussion of what happens to stars when they run out of fuel, because what that really means is stars that no longer have this hydrostatic equilibrium available. So keep that in mind as we continue through this week and more into next, that hydrostatic equilibrium means everything is nice and in balance and the star can be stable, but we're going to talk about what happens to stars when they're no longer stable and in balance. But that's our entire discussion of the really key pieces of Chapter 21 that we need for this week. So I'll see you in the next video.